let's finish this example. We have obtained the values for C1, C2, and C3. Now let's find the inverse Laplace transform. To find the inverse Laplace transform, then let's first introduce two formulas. The first one is the Laplace transform of a constant a times exponential minus a times t times cosine omega t the Laplace transform is a times s plus a over s plus a squared plus omega squared. The second formula is the Laplace transform of the constant b times exponential minus a times t times sine omega t is b times omega over s plus a squared plus omega squared. Since we know the Laplace transform is a linear operator, then we can apply the rule of superposition. That is, the Laplace transform of the two is the sum of the Laplace transform. That is, the Laplace transform of a times exponential minus a times t times omega cosine omega t plus b times exponential minus a times t times sine omega t is a times s plus a plus b times omega over s plus a squared plus omega squared. So we don't need to worry about the first term. And we don't need to worry about the coefficient minus 3 over 5. So we can write this part in this form. then we can apply the inverse Laplace transform. Then let's do so. We have s plus 2 over s squared plus 2 times s plus 5. Let's first work on the denominator. The denominator can be written as s squared plus 2s. Let's write 5 as 1 plus 4. Then we know for the first 3 terms, it is a complete square. It is s plus 1 squared. Then for the second term, it is 2 squared. If we compare to the denominators here, then we know the value of a is 1. Then omega is 2. Now let's work on the numerator. So we have s plus 2. Since the value of a is 1, so let's write s plus 1, then plus 1. Since omega is 2, let's write 1 as half plus 2. The 2 is omega, 1 is a. Then we know here the capital A is 1, then capital B is half. Now we can apply the inverse Laplace transform to this form of the Laplace transform of output. Then we have the constant 3 over 5. And the coefficient will be the same, minus 3 over 5. The a is 1 here, and b is half. Omega is 2. We have cosine 2t, sine 2t. Then exponential minus t. This is a time function. Now let's summarize the procedure we did for a complex function, a rational function with a pair of complex roots. So we have the numerator in S. Let's assume the denominator has the term S plus P1 times S squared plus AS plus B. Let's assume S squared plus AS plus B has complex roots. Then it can be written as the partial fraction expansion form. This will be C1 over S minus P1, then plus C2S plus C3 over S squared plus AS plus B. Then to calculate the coefficient for C1, we can still use the cover-up method. Then for C2 and C3, we have to use the method by balancing the coefficients of the equation. Then for the case of purely imaginary roots, when A is 0, then in this case, A is 0, then B is greater than 0. Then S plus B has a pair of imaginary roots. This will be B, J minus BJ. In the complex plane, the real part, imaginary part, sorry, here it should be square. So we have here square B, and here minus square B. In this case, the calculations are the same. Now let's summarize the time functions associated with roots in the S-plane. Now let's look at this figure. First, let's look at the real roots. If we have real roots at the left half plane, then based on the inverse Laplace transform, the corresponding time function is exponential minus AT. It is a decaying exponential function. If the root is further to the left, the decaying is faster. that's a case of these two figures. However, if the root is in the right half plane, then it is a growing exponential function. If the root is further to the right, it grows faster. That is the case for these two figures. If the root is 0, then the time function is a constant. It is a step signal. Then let's look at the case of complex roots. If we have a complex root in left side plane, then based on the inverse Laplace transform formula, then we have the exponential function, decaying exponential function times the sine function or the cosine function. Then it will be a damping function. In this form. Then for the case, if we have imaginary roots, then the time function will be sinusoidal waves. If the imaginary roots is to the top, then the frequency of the damping is faster, higher frequency. That is a case of these two figures, these two plots. Then if the complex roots are at the right half plane, then it is a growing exponential function times sine function or cosine function. That will be this case. It is a growing oscillation. So this plot, this figure shows the time function associated with the locations of the roots in the complex plane. Now let me give you some time to do this exercise. It is a midterm exam question last year. The question is to ask you to find the time function by assuming the input signal is known. For example, let's assume the input signal RT is a step signal. Then the first step, you need to calculate the Laplace transform of the input. Then you use the partial fraction expansion to find the time function for Ys. Then that brings us to the end of this topic on how to calculate the time function for general input signal